state average.
Yeah, for individual state, if I try to construct density using the orbitals from state averaged orbital optimization, then this density will be incorrect, of course, because it will not produce, for example, the correct dipole moment. I need to include orbital response, of course, in the calculation of the density for the individual state, and then I will obtain correct dipole moment, correct energy gradient, and everything.
Oh, okay.
So this is exactly the same feature as is present in the state averaged CAS SCF methodology. All right. Let me move on.
Shall we take a break for 5 minutes?
All right. If yeah,
let's take 5 minutes break. I think this is a good moment.
Okay, let's take a break.
Yeah.
Geometries as well as, of course, energies of the ground state, equilibrium geometries of the ground state species. Yeah, that's correct.
So what he's telling us is that there are cases where the Kohn-Sham theory fails.
Right.
That dramatically, then his method will save this. So there are many, we can find such cases, and also especially his method is useful for the excited state where we have many such open cases. For the ground states, I think majority of the ground state we are dealing with is mostly closed shell. So typical Kohn-Sham theory should work. I would say something like more than 70 to 80% of I think that it's probably okay. But some of the transient state you just mentioned, sometimes it could have a really open shell case, then Kohn-Sham would fail to give you the right number. Yeah, so there are some cases. So his method is more general.
Right. Okay. Are we ready to?
Let's go. Let's go. Right. But please finish within 15 minutes, not okay. 16 minutes.
I will try. I will try.
Please.
Right. In the following, I will describe some applications of the REKS methodology to excited states. And one of the first, reasonable applications would be to check how accurately the method can describe energies or vertical excitation energies of well-known molecules. There are several sets of, vertical excitation energies for organic molecules. For example, I calculated excitation energies for these 15 molecules by taking the best theoretical estimates from compilation by Walter Thiel and others. And as a matter of fact, the state average REKS and SSR method, they work with approximately the same accuracy depending on the density functional or the basis set as the standard linear response TD-DFT for the molecules at their equilibrium geometries, of course. So, and this is good because we can describe excited states of these molecules at their equilibrium geometries with approximately the same accuracy as the linear response TD-DFT. And everybody regards, many researchers regard that accuracy of linear response TD-DFT for vertical excitation energies at the equilibrium ground state geometries is fairly good. But REKS can do more. I already showed you dissociation of hydrogen molecule where TD-DFT fails to correctly describe the potential energy curves of the ground and excited electronic states. The dashed curves, dashed lines show potential energy curves obtained by TD-DFT, which converge to the same energy in the limit of fully dissociated bond, whereas REKS produces correct shapes and even accurate shapes of the ground and excited electronic states. And this failure of TD-DFT is associated with the single determinant nature of the reference state, Kohn-Sham density functional theory. So this is single reference state, single scalar determinant. It cannot describe correctly the bond dissociation, and therefore, if we try to describe excited states as a response of the wrong ground state, we obtain wrong energy. Besides this dissociation of homonuclear molecules such as H2, REKS can describe dissociation of, say, heteronuclear molecules such as lithium hydride. So lithium hydride around the ground state equilibrium geometry is, the ground state is ionic. However, the lowest excited state of lithium hydride will be covalent. Say, will have a covalent, say, nature, covalent characteristics with a diradical electronic structure near the equilibrium geometry. However, as we stretch the lithium hydrogen bond, we end up in the ground electronic states with two neutral atoms, lithium and hydrogen, with unpaired electrons, of course, on each of the atoms in the limit of dissociated bond, fully dissociated bond. However, in the excited electronic state, we end up with positive lithium cation and hydrogen anion. All right, so this excited state will become ionic in the dissociation limit, although the excited state was covalent near the equilibrium geometry. And the opposite is true for the ground state. Ground state was ionic near the equilibrium geometry, and it becomes covalent near the at the dissociation limit. This means that there is avoided crossing between the ionic and covalent states along the dissociation curve of this molecule. And this avoided crossing is correctly described by REKS. So these dotted lines, they give energies obtained by EOM CCSD and the ground state from CCSD. As you see, the solid lines give REKS energies, dotted lines CC and EOM CCSD, and dashed lines give what TDDFT produces. So TDDFT produces incorrect dissociation limit for this molecule, well, unsurprisingly, because the ground state is wrongly described, and as well as the excited states are not, excited state is not correctly described at the level of time-dependent density, linear response time-dependent density functional theory. So for some other interesting systems, such as extended pi conjugated systems, polyacines, which are molecules made of several fused benzene rings, there may be as many as 20 or more fused rings in these molecules. Up to 9 rings were synthesized. Probably even now they have with 10 rings, polyacines. But in theory, they can be extended up to infinity. And these molecules, they have strongly correlated singlet ground electronic states. The experimental data were obtained up to n equals 9, so 9 fused rings. And from the experiment can only be, well, the experimenters are confident that the ground state of nonacin is singlet. Although one may expect a very low singlet triplet gap in longer polyenes. And these states, they have a strongly correlated nature because you can break, here I show it for pentacene, you can break some of the double bonds, creating diradical state and recouple other pi bonds such that you have radical pair, or radical pair here, the central ring, or at the some middle ring, or at terminal ring of the molecule. So that will be kind of roaming radical pair across that chain of fused tangent rings. So, and for these molecules, TDDFT yields excitation energy to the lowest excited state, which is described by HOMO to LUMO 1 electron transition. The energy of this state goes to 0 gradually as we increase the number of fused benzene rings. For 20 benzene rings, it becomes near 0. However, from the state average or SSR calculation, we obtain finite excitation energy, which is pretty close to experimental estimate. I should say that experimenters know only up to nonacin, up to this molecule, and they simply extrapolated this dependence to infinitely long chain. So this may be not very accurate experimental estimate, but nevertheless, it remains finite. That's the most important fact from the experiment. And REKS produces finite excitation energy even for the longest polyene. So the other advantage of REKS methodology, I already mentioned this, that it is capable of describing conical intersections and avoided crossings between the ground and excited electronic states. So this is again a picture showing conical intersection, double Kohn topology, and this would be avoided crossing if the coupling between the states would be non-zero. However, at the tip of conical intersection, we should have coupling between the states 0 and equal energies of the two crossing states. So REKS is capable of describing these states correctly and also producing the branching plane vectors. So we can obtain branching plane vectors as gradients of energy difference of the diagonal term and gradient of the off-diagonal term, like it is shown here. And if we plot potential energy surfaces of the ground and excited electronic states in these coordinates, for example, for famous PSB3 molecule, this is shown here, we obtain the double cone shape near the crossing point, near the tip of the crossing point. So the two states cross only at one point here in these coordinates and nowhere else. And this is correct description. So here we can, I showed that we can construct basically the branching plane vectors of.
Let me have a question. So is that right. The H is the non-adiabatic coupling?
Not exactly. This is one of the. This is what is it? It's a gradient difference vector and coupling strands gradient.
Yeah. So it's
this is coupling strands gradient. To obtain non-adiabatic coupling, one needs to combine both vectors, the energy difference gradient and the coupling gradient, in one expression. So this will give non-adiabatic coupling. Mm-hmm. This expression gives the non-adiabatic coupling between the two states. So, but knowing these two derivatives, basically they obtain from the derivative formalism, analytic gradient formalism for the REKS method, one can easily calculate the non-adiabatic coupling between the two states.
So this is an advantage, right? Because of you expressed it the 2 by 2. Yeah, so this kind of coupling is automatically appears. Otherwise, and in that theory, you have to develop, you have to derive the gradients or something like that. But,
right. Sometimes, for obtaining non-adiabatic coupling, one needs to take to calculate energies and let's say wave functions or quasi-wave functions at several geometries before finding the non-adiabatic coupling. Yeah. But here we can do all the calculations at one and the same geometry by simply reusing some parts of the gradient of the analytic gradient for ground and
already there. That's already there.
Mm-hmm.
Yeah. Okay.
Right. So the standard linear response TD-DFT. So here we see the geometries, superimposed geometries of conical intersection in ethylene, twisted pyramidalized conical intersection in ethylene molecule. So this conical intersection mediates the ground and excited states. In principle, one can optimize crossing, minimum energy crossing point by using time-dependent linear response, time-dependent DFT method also. However, if this crossing will not be, I mean, this is only the geometry, but the crossing produced by time-dependent TD-DFT will not be conical intersection, but linear intersection. If we calculate energy differences between the ground and excited state around a loop, within the branching plane of this conical intersection, the energy difference should always remain positive, right? Because the two states can cross only at one point, so here in the middle. But if we calculate around a loop of certain small, very small radius, very small but finite radius, then we will obtain always finite energy difference, nowhere zero. However, the energy difference from linear response TD-DFT, which is shown by dotted line here, it crosses the zero line twice, which means that it produces essentially linear intersection and not conical intersection between the two states. So this, again, is a failure of time-dependent TD-DFT, which is associated with its linear response nature, that the ground state is the reference state, the response of which we calculate to obtain the excited states. And the ground state, the reference state, is, by virtue of the Brillouin theorem, is decoupled from the excited states, from the response states. And this leads to the fact that the matrix element between the states, the coupling matrix element, is always zero. It is always zero, and not only at the tip of the conical intersection. So it should be zero if we have proper conical intersection. It should be zero only at this point, and at all other geometries it will be non-zero. But linear response TD-DFT yields it zero, and therefore only one condition needs to be fulfilled to have the two states crossed. All right, so as I said, this is a failure of linear response TD-DFT. And regarding the accuracy of description of the conical intersections, I can show you in the slide. So the geometry of the conical section and potential energy curves of the ground and excited states, they are not distinguished by color, they simply crossing points. So these blue, in fact, these are blue lines show REKS energy curves, state S0, state S1. Greenish, these green curves, multi-reference CI, CAS SCF red, and dashed lines show quantum Monte Carlo again. Quantum Monte Carlo for the lowest energy state and for the next state. So along certain paths in the geometry, so called bond length alternation path. So we invert essentially length of the formerly double bonds and single bonds along this path. These geometries were obtained by Massimo Olivucci quite some time ago from CAS SCF calculations, of course, but typically these geometries along this path used to test various methods for their ability to describe conical intersections. And as a matter of fact, CAS SCF produces crossing between the ground and excited states at this geometry, essentially at zero bond length alternation, which means that lengths of double bonds and single bonds are equal. Multi-reference CI shifts towards positive blah values, somewhat shorter double bonds than single bonds. However, REKS produces it there, crossing between the two states, even at greater value of the bond length alternation. And this crossing point is very close, both energetically and geometrically, to the crossing produced by quantum Monte Carlo. So again, these two methods, CAS SCF, MRCI, singles and doubles, they are not exact. These are not exact methods. They are wave function methods. These are probably quite good for some qualitative descriptions of some things, but they are not equally good for quantitative description. However, REKS can produce both qualitatively and quantitatively correct geometry and energy of conical intersection, at least for these molecules. We also have compared energies and geometries of conical intersections for other molecules, where of course we don't always have reference reference data from quantum Monte Carlo, we used multi-reference CISD, but REKS is sufficiently accurate compared to MRCISD as well for the geometries of conical intersections. Right, so this method enables us to calculate accurately the geometries of conical intersections and the excited states of molecules with dissociating bonds or with multi-configurational ground states. So these are quite big advantages of these methodologies. So in fact, the methodology which I have described with two states included into state interaction, so perfectly spin paired and open shell singlet states, can be further improved by complementing the two states, perfectly spin paired open shell singlet, by doubly excited electronic configuration. The difference between these and that is that the two states, let's say with orbital A W occupied, orbital B empty, orbital A empty, orbital B W occupied, they are coupled with exactly opposite or interchanged coupling coefficients compared to the perfectly spin paired singlet state. So imagine that in the perfectly spin paired singlet state, we have only, say, C1 equals 1 and C2 0. Then doubly excited state will have C in front of, let's say, ground electronic configuration with orbital A W occupied 0 and 1 in front of doubly excited electronic configuration. I show both orbitals degenerate simply to save some space, but imagine that this orbital is above orbital A. This is HOMO, this is LUMO. So then the doubly excited state will have only this electronic configuration with LUMO W occupied, HOMO empty. So this is indeed doubly excited state. For multi-reference situations, the two configurations will be, of course, mixed with certain coefficients, but they still remains double excitation with respect to this state. So in this space of three states, I can again construct the secular equation for the state interaction method. I include